In this video series, I will present a few tools I created to help engineers understand the concepts behind digital signal processing, DSP. Starting from the basics of a discrete Fourier transform, discussing concepts such as aliasing and leakage, and well, the whole reason why I created these tools is because I find it teaching this concept with slides and videos in a quick and intuitive way is very, very hard. These tools are meant for test and measurement engineers, signal analysts, basically anyone who works with DSP tools and wants to get a better feel of how sampling rate, frequency resolution, window overlap, and all of that stuff is affecting your results. Sure, there are a lot of videos and resources online showing you this, that, and everything in between. But at least for me, they often end up making things more confusing than they actually need to be. I don't care about integrals. I don't care about negative frequencies or any of that imaginary nonsense. I'm here to talk about real signals, the kind you pick up from a microphone or an accelerometer, physical stuff, vibration, sound, movement, things you might want to analyze with an FFT or spectral analysis or whatever you want to call it. So those are the tools I created, and here's how to use them. All right, starting with the Discrete Fourier Transform demonstration tool. In this tool, we have two graphs. On the top, I have the time domain signal, and in the bottom, I have a spectrum. On the top graph, I have a sinusoid in red. This is an analog signal that I am sampling the samples in yellow. We can control the frequency of this signal with this slider. And of course, below you will see the spectrum updating. The lowercase x that you see here are the amplitudes of the samples that I am acquiring. These amplitudes are then fed into a DFT calculations. Here they are to calculate the value of the spectrum of the spectral lines, DFT bins, whatever you want to call it. So n is the index of each sample in the time domain. K is the index of the DFT bins. J is just the imaginary stuff. And that's all we need to calculate the DFT. So the summation here goes from 0 all the way to my last sample. In this case, I have 8 samples, but since I am starting from 0, I go all the way to 7. And why I have 8 samples? Because I am sampling this signal at a ratio of 8 Hertz. I have a 1 second time frame, observation window, whatever you want to call it. And during this 1 second, I acquired 8 samples. The easiest example that I always like to start with is to calculate the value of the DFT bin for 0 Hertz. That is the easiest because at 0 Hertz, this K index is 0. So this guy is 0. E to the power of 0 is 1. So all I am left with is the summation of the amplitudes of all of my time domain samples to calculate the value of this particular DFT bin at 0 Hertz. On the spectrum, you see that my 0 Hertz component has no amplitude at all. And graphically, we can very easily see why in this example. This sample here is at 0 amplitude. I have 3 samples above, so positive samples, positive amplitude samples. I have some negative amplitude samples. If I sum all of the samples, I have an amplitude of 0. That's what you see in here, right? For 0 Hertz, I am just doing a summation of the amplitudes of all of my samples in my time frame, in my observation window, multiplying that by 1, and that is the value of my spectral line. Of course, 0 Hertz is a special case because there is not a complex number, but anything above 0, then this component here will be a complex number. That's why you have phase and amplitude or real and imaginary part for the values of your spectrum. In this case, I am only plotting the magnitude Just to keep things simple, on my next tools, I then introduce the concept of phase, and then we can play around with that later on. Nice. So based on the index value of each DFT bin, I can calculate what is the frequency of that particular bin or spectral line. Just need to multiply that index by my sampling frequency and divide by the number of samples that I acquired. So for example, let me move this index. Let's take the example of x of 2. So k is 2 times 8, 16 divided by 8 is 2 again. So the frequency for the bin 2 is 2 Hertz. If I change the number of samples by increasing the length of my observation window, I increase it to 2 seconds. 2 seconds here, I have double the amount of samples. So now I have one DFT bin every other 0.5 Hertz, and this is what you see here in this frequency resolution parameter. It is just the sampling frequency divided by the amount of samples that I acquired. And now at this particular example, I have a bin at 0.5 Hertz, another at 1 Hertz, another at 1.5 Hertz. So the K value here is not really your frequency necessarily, but it's just the index of the bin itself. And you convert from the index to the frequency using this formula. Frequency resolution. The only way that I can get a finer frequency resolution, so a lower value for its frequency resolution, is if I increase the time, the length of my observation. Many people, especially at the beginning, they think, if I increase my sampling rate, I can increase the frequency resolution of my spectrum. You can see that that is not the case. Why? Because, well, let me go back to my observation window of 1 second. I have a sampling rate of 8 Hertz. So in 1 second, I acquire 8 samples. If I use a higher sampling rate, 100 Hertz, in 1 second, I would acquire 100 samples. And wouldn't you know, 100 divided by 100 is still 1 Hertz. So the only way that you can decrease this value here is that you increase the ratio between the number of samples you acquired to the sampling frequency. And the only way that you can do that is, again, by increasing the observation time. Okay, another important concept that we can observe in this too is the Nyquist frequency that I have here annotated in my graph. Nyquist is just half of your sampling frequency. And this is a very important parameter because it tells you what is the highest frequency that you can uniquely resolve in your spectrum. Seems complicated, but well, let's look at it graphically. That's why I created this too, so we can visualize this graphically. What I will do is I will increase here my x-axis with this button. We'll increase it again. And first things first, if you look at the Nyquist limit, all the bins above that, they are just a mirror of your bins below that frequency. Frequency content that you see above Nyquist, if you remember from school or college, those are the negative frequencies mirrored across 0, all of that nonsense. Come on, negative frequencies. Who has the time to deal with that? So yeah, we just ignore these guys. No negative frequency for us in the real signal, and no frequencies above Nyquist. We don't care about it. And the funny thing is that the DFT cannot distinguish between those frequencies and those frequencies. Don't believe me? Well, let's give an example. Let me reset the displays. Let me increase K by 4. Here I am calculating the spectrum out of a 1 Hertz signal. It is nice that I have a component, a spectral line at 1 Hertz. Check that I also have another component at 7 Hertz. My signal, my original signal is 1 Hertz. It doesn't have any 7 Hertz component on it. So why is this happening? Well, as I mentioned, the DFT algorithm cannot really distinguish between a 7 Hertz component and a 1 Hertz component. Don't believe me? Well, let's just try to increase the frequency of my signal all the way to 7 Hertz and look at this. Now, well, this component is correct, but this is not. Why do I have this component? You can visualize on the top graph. I'm just not sampling my signal fast enough to capture these ups and downs of my sine wave going at 7 Hz. So the DFT is just seeing these amplitudes of my samples, and well, if you do the calculations here, you would see that the resulting amplitude for 1 Hz or 7 Hz signal is exactly the same, at least at this particular sampling rate. If you want to resolve higher and higher frequencies, you need to acquire your signal with higher and higher sampling rate. So the only limiting factor here on the highest frequency that you can visualize on your spectrum is your sampling rate. You can try all you want to make your time frame bigger, but the result of that is just that you have an intermediate bin here at 0.5 Hz, but you are still seeing a component at 1 Hz and another component at 7 Hz. So the only way to resolve this higher frequency component is to acquire the signal with higher sampling rate. In this particular phenomena that we are seeing here, that, well, we have a 7 Hz sine wave, but spectrum is showing me 1 Hz component. This is called aliasing. To avoid this type of error, we normally apply a filter to our signal above Nyquist. So all the frequencies above Nyquist, they are attenuated such that we don't have this mirroring effect in our spectra. So before you even do the sampling of your signal, you need to apply some sort of filter to the data such that when you go to sample your signal, you are not committing this crime here, this mistake of sampling data above Nyquist. Before you actually sample your signal, all frequencies above Nyquist are removed from your signal. So you don't have this 7 Hz component appearing on your spectrum as a 1 Hz component. This will not happen because of the anti-aliasing filter. And that is also why normally when we view spectra, we only view it up to Nyquist. If we measure a particular microphone signal, accelerometer, and so on, it doesn't make sense to look at frequencies higher than Nyquist. That's why we cut the spectrum usually when you display the data at Nyquist, or even below that, depending on the anti-aliasing filter that you use, but that's another discussion. Finally, the last thing that I want to show is that you can keep on increasing this K all you want, just to showcase that, well, the DFT itself, it has this periodicity, and we could try to calculate bins with a higher index, but the signal here, you can see graphically, it is just repeating itself after you surpass the index for your bins of the index of your samples in the time domain. So if I have 8 samples in the time domain, I can only calculate 8 spectral lines. I only have 8 DFT bins. And well, half of that we ignore, we only display half of that. And then it depends on how many samples you have. If it is an even number, normally you display your spectrum all the way to half of the number of samples. If I make my observation time frame a little bit bigger, such that now I have 9 samples, this is an odd number of samples, I will not display that extra spectral line. Why is that? Because you can see here that this spectral line, X5, has exactly the same amplitude of X4. So it is mirrored across Nyquist. It is not really new information. It is not adding anything to us as data analysts, as NVH engineers. So we just ignore anything above Nyquist. And that is pretty much it for this too. There are many more things that you can discuss, showcase, but this is the basics of it.